All right, so we left off last time doing the telescopic collapsing series, right? And I think we've seen enough of those now that we can move on. I hope you've seen enough. All right, so I want to do a summary of where we are before we move ahead. We have right now the nth term test. And that's where we look at the part inside the series, right? This piece. And we let n go to infinity there, right? And as we look at this, if that goes to something other than 0, okay? So if it goes to something with a little line through it, other than 0, what do we conclude? This will diverge. Then the series diverges. I'm just going to put div. But if that limit goes to 0, the test fails completely. So that's one way we know how to deal with series, is doing the n-term test. The next thing that we know about series is that it could possibly be geometric, right? And with geometric, all we have to do is identify, we have to make it look like the geometric formula first, and then identify what A and R are, what A and R are. Yeah, you know what I mean, right? Identify A and R, and then if the absolute value of R is less than 1, it converges. If it's greater than or equal to 1, it diverges, right? But geometric series is kind of the next thing we had. Then after that, we had harmonic. And what's good about harmonic? They always diverge, right? Harmonic series always diverges. What is it that makes the series harmonic? What are you looking for? Constant linear function on the bottom. That's what you're looking for, all right? In that case, you pretty much conclude that it's going to diverge. And then we had telescopic. How do you go about doing telescopic? Okay, so you write out you try and get a pattern. Sometimes that required partial fractions. On the quiz, it was what? The property of logs. And then you get subtraction somewhere in the sum. Then you write out the nth term, right? The nth partial sum, S sub n. Get your pattern of cancellation, then take the limit as n goes to infinity, and you get your solution. So with telescopic, I'm going to circle these. Telescopic and geometric. If those converge, right? If they converge, we usually can give the actual numerical answer of what it does. Did this one converge, the quiz? Anyone got it? Did it converge? No one wants to. Yeah, I believe this one diverges. Because you take a limit at the end. You let n go to infinity, and you have natural log of infinity, which is infinite, so it should diverge. But I'll look through it again. I think that's what happens. So if these do converge, then we should be able to get some numerical answer for them. So today we pick up and we have more stuff. This is actually chapter 8, section 3, so I'll just let you know where we are in the book right now. This is called the integral and comparison tests. And see if I have one of those formula sheets. Everybody have their little sheet handy with all the convergence tests on them? I don't know where mine is, but it might be in here. There we go. Yes? Okay, so on your sheet, the integral and comparison tests are right below the P-series. We haven't talked P-series. We will talk P-series after we do this, all right? So here's the motivation. We're going to start with the integral test. Do you remember from last class what our main goal is for this whole last lecture or so? Does a series converge or diverge, right? The integral test is another way of determining that. One thing, though, about this integral test is that our conclusion at the end is that it either converges or diverges. The integral test will never, ever tell you what it converges to. So if it converges, we won't be able to say, oh, it converges to 1/2. We'll just be able to say it converges. And for where we're headed with this, that's often good enough, all right? That's all we need. So here's the way the test works. Let's say you have a sum, right? N equals 1 to infinity, a sub n. We know that this means a1 plus a2 plus a3 forever. So that's what a series is. And if we look at this geometrically, we said that you could almost look at it like a function, except that it's not the entire function, it's just dots on the function, isn't it? So what I'm going to do is just draw like at 1, at 2, at 3, at 4, just draw some dots. Now, I'm going to draw them in a certain way. I'm going to draw these dots so that, notice that a sub n is greater than 0 for all n. Remember that little upside down capital A meant all n? Notice that, so that means, notice that every one of these points is positive, right? Above the x-axis. And then also notice that a sub n is decreasing. Meaning that as you move from left to right, each dot gets lower than the one before it, right? Lower, lower. So these are going down, yes? But it can never cross the x-axis because they all have to be positive, right? So in other words, this sequence of dots is going towards 0, isn't it? It's headed towards 0, which is what we need for any series to converge, don't we? We need the sequence to go to 0. If it goes anywhere other than 0, it diverges, and term test. So we know that the series that we're interested in are going to have to behave something like this. Now, being positive is not necessarily always going to be the case, but let's just say it is. Then do you agree that if we can somehow rewrite a sub n as a function instead, I'm going to put f of x. I'll do it this way. If we convert a sub n to f of x on reals. So we did this before. Remember when we were trying to do L'Hopital's rule on a sequence, and we couldn't do L'Hopital's rule because a sequence is not a continuous function? So what we did is we said, oh, there's a theorem that says if whatever the function does, the sequence must do also, right? We're going to do the same sort of thing here. We're going to say, look, instead of looking at that sequence, just the dots, let's fill it in as a function. If we fill this in as a function, I don't know what the rest of it does, but it's going to be decreasing also, right? The integral test is saying this. The area underneath this curve, right, that area should be bigger than the sum of each of the dots, shouldn't it? Because when you take each dot, you're taking its height, aren't you? You're measuring its height. And then when you add the next one, you're measuring the next height on top of that and on top of that. Do you agree that the sum of all these black heights should be less than the area under the entire thing? Does it make sense to you that that would be true? Yeah? So the integral test says, look, if the integral of this thing converges to a number, then the series must converge. Would that make sense to you? If the area under here, the blue, is finite, then the series must be finite also. Okay? Now the other way, the other part of what the integral test tells us isn't as intuitive. It isn't as clear. But this is just the geometric kind of setup, so you get in your mind like what's happening. Now let me actually write down what the test is, or actually you have it right here, right? So let's see what the integral test says. So you have a series, right? It says series n equals 1 to infinity a sub n. And then below it, it says a sub n. They write a sub n equals f of n. Do you all see that on the test? Does anyone not have this? Everyone has it? Okay. What this statement in this test on this sheet means is they're converting the function, they're converting the sequence to a function. So it is implied here that f of n really means like f of x. They're extending it to all the real numbers instead of just the integers. And they say, next step, or next part, part 1, converges if what? If the integral from 1 to infinity of the function of x dx converges. So that's what I was just saying. If that area under there is finite, then that means that the original series converges. The next part, part 2, is not as clear. I think you could argue with me like, hey, does that always work? It says that if this area diverges, which means if this area is infinite, the series must diverge also. Do you swallow that one as easily or no? I mean, think, what I'm saying is, look, this blue area is infinite. Does that mean that that black, all those black lines added up together has to be infinite? I don't know if you could convince yourself it has to be true, but it's a test. It's been proven. All right, we're not. I can't convince you easily. All right, we'd have to go through a formal proof of the integral test, which we're not going to do. So this is a very powerful test because we can integrate, right? Hopefully. And if you can integrate, then you should be able to run this test. But there are some conditions. Notice in the comments box over here. Okay, the function f obtained from the sequence must satisfy these conditions. It must be a continuous function. That means you can draw without picking up your pencil, basically. It must be positive. What does that mean? Above the x-axis, right? Must be decreasing, must be going down, and the last part, it must be integrable. That means you need to be able to integrate it, right? You can't integrate it, you can't use test. So when we have a problem with integral test, we have to first confirm that the function that we are going to convert it to satisfies all these conditions. On an exam, if you run an integral test and you don't show that the conditions are met, you're losing points. I told you all a while back that part of what makes this whole thing kind of weird on exams is that you have to express your ideas on the page clearly so somebody reading it can say, oh, they're running an integral test. Okay, they're making sure it's continuous. Okay, they're making sure it's positive. Okay, they're making sure it's decreasing, right? Once you meet all the conditions, then you can run the test. But without meeting the conditions, you're hoping that this is the right test to use. So let me give you an example. All right. Yes, thank you. Exams. No, I'll take it here. The exams are right there. All right. Here we go. So the first example we're going to do is, does the series sum n equals 1 to infinity of n over n squared plus 4 converge or diverge? Do y'all remember what my hint to you is on an exam, that it's either going to be geometric or telescopic? What I'll ask in the question? I'll in some way ask you what it goes to. Like I'll say find the sum. On a test, if I say find the sum, that means you can find the answer. In this one right here, I'm not saying find what it converges to, am I? It just says tell me if it converges or not. I don't care if it does converge what it goes to, just tell me yes or no. So this is where you take out a coin and you flip it, converge, and you just write it down, right? Converge. And then you move on to the next problem. We got to see some work. All right, so let's start running through all the different things. Nth term test. Nth term test. So I'll show a lot of detail on this one. I'm letting everyone know. When I say everyone, I'm letting the reader of my work, right, understand what I'm about to do. I'm going to do an nth term test. So I'm going to take a limit as n goes to infinity of n over n squared plus 4. That's infinity over infinity, right? We can apply L'Hopital's rule. We all understand by now that we would really have to convert it to a function of real variables, but there does come a point where we just kind of say, we get it, okay? We understand what we could do. Remember, you can use an L or an H here, just as long as you represent it somehow that you're using L'Hopital's rule. Derivative of the top is 1, derivative of the bottom is 2n. And that goes to 0. What does that mean? Test fails. All right, so then we look at it. All right, we had what next? Geometric. Is this a geometric series? Why or why not? Yeah, you have to have an n and an exponent for it to be a geometric series. N has to be up there as a power. It's not there, so it's not geometric. Is it harmonic? Yeah, the bottom is not linear, and so it's not harmonic. How about, what was the next one? Telescopic. Maybe. But what we used for telescopic was we had to get it to somehow become subtraction, didn't we? And so we used partial fractions for something like this, like when we had a rational function. You cannot factor the denominator. This is an irreducible quadratic, basically. And so the whole goal when you have an irreducible quadratic, if you remember back from partial fractions, is when you have an irreducible quadratic, you're trying to rewrite it where you have a linear expression on top of the irreducible quadratic, which is exactly what we have here, a linear over a quadratic. So there's nothing you can do, even with partial fractions, that would make that any nicer. So that you kind of throw that out the window. And so then you start looking at it, and this is where integral test starts coming from. You look at this and you say, could you integrate that? Like imagine this was, x over x squared plus 4. Like, could you integrate that? Do you see the integration? Basic substitution, wouldn't it be? Right? If the bottom is our u, the derivative of that is up top. We're off a little bit, but we can handle that. So now I'm thinking, integral test, because I can integrate that. But I now need to make sure I satisfy the conditions for the integral test. So after ruling out everything else, I'm now at integral test. All right, so conditions. I'm gonna write down. Let me ask you: would you like me to keep n as our variable, or would you like to just go ahead and make it all x's? I don't care. You should be comfortable both ways. So n or x? Yeah. Really? Okay. I'll do x then. Let f of x be a sub n on reals. So this is just to explain, again, to myself and to everyone else what I'm doing. I'm letting f of x be the function that is the sequence that we're given here, but on the real numbers instead of on the integers. First conditions. All right, first condition. What does it say here in our comments box on the side here? Must be continuous. Is f continuous? Well, f of x is equal to x over x squared plus 2. Is it continuous? Is it 2? 4, sorry. So that is the extension of our sequence into the real numbers. Is that a continuous function? Yes? Why? You will never get division by 0, right? This is a rational function. All rational functions are continuous on their implied domains. This is Cal 1. All rational functions are continuous on their implied domains. As long as the denominator is not 0, you're in business. And even if it was 0, as long as it's not 0 where we're looking from 1 to infinity, aren't we? That's where we're going to look. So let's say that this had been over here, just for the sake of demonstration. Let's just say this would have been not x squared, it would have been x plus 4. Of course, we would have been looking at a different approach probably, but the discontinuity would occur at -4, and we wouldn't be concerned about that because we're looking over at +1. Okay, so is it continuous? Yes. All right, second condition. Yes, but you must write it, okay? If you justify it even better, if you write down like yes because this, that's fine. But what I'm looking for is that you at least addressed it. All right. This is very much like writing a paper. I'm looking for like what do they call it, like MLA style or whatever. You know, there's certain ways that you want to construct your logical, thoughts on paper. It's not so much anymore just get the answer. It's can you express it in a way that somebody can read it? Right? Think about a job that you're working with, engineering firm or something. You get your work together, you're working on a project, you have to go present that to your team. If it looks like shit, then, they're not going to be able to read any of it. It's like you need to get good at expressing yourself legibly and clearly. It's a skill. It takes time to acquire. All right, so conditions, first one. Second one, what do we need? Is it positive? Is this function positive? Well, this I better show, okay? Is this greater than 0? Is it? What can you tell me about the denominator? It's always positive, right? So this is the same as really just asking when is the top greater than 0, because I already know the bottom's positive. As long as the top is positive, the whole thing's positive, right? So is this going to be true? Is x always greater than 0? Where we're looking, yes, right? Where we're looking from where? 1 to infinity. So this is true on the interval 1 to infinity. Why are we starting at 1 and ending at infinity? Well, not ending, but why is our interval always 1 to infinity? Because it's a sequence, right? The sequence always started at 1, a sub 1, a sub 2, a sub 3. So we always went from 1 out. Okay, so that's clear. Third thing, what do we need? Decreasing. Is f of x decreasing? Well, we know how to show a sequence is decreasing, don't we? Last time we did that, last class, or maybe it was the one before. The one before. So what I'm doing right here is I'm actually going to accidentally flipped the page there. I'm going to split this into two pieces because there's two different ways to show that this is decreasing. I'm going to show you both ways. All right? The first way to do this is to look at the sequence itself and to show that a sub n is greater than a sub n plus 1. Isn't that what it meant to be decreasing? Or sequence to decrease? If I can show that that's true, then I will have satisfied the condition. Damn, I just bit myself. And then that has nothing to do with the function. That's the sequence itself. But whatever the sequence does, this function should do the same thing. What is another way we can show that a function is decreasing from Cal 1? How do you show a function is going down in Cal 1? What do you look at? Negative slope. The slope is the what? How do you get the slope of a function? Take the derivative. So if the derivative is negative, then it's decreasing, right? That's the other approach. So my other way would be to show that the derivative is negative. Very different approaches. They both accomplish the same thing. Sometimes doing it the way on the left is easier. Sometimes doing it the way on the right is easier. So let me try the one on the left first. And then we'll see what we get, and then we'll do the one on the right, and we'll convince ourselves it's decreasing. So a sub n is n over n squared plus 4. I need to show that that's bigger than n plus 1 over n plus 1 squared plus 4. Right, so that's rewriting the sequence, replacing n with just n, and then replacing n with n plus 1. And you cannot just do that and just be like, yep, that's obvious. You know, you have to do a little more. So I'm going to multiply out the bottom. So when I multiply this out, I get n squared plus 2n plus 1. Then I add 4 to it. So I get n squared plus 2n plus 5. And then you could do some sort of like cross multiplication here. If you want to call it cross multiplication, it's kind of dangerous to say that, but multiplying both sides by the LCD is what you're doing. We do have to always worry, because this is an inequality, that when you multiply both sides of an inequality, you have to be real careful that you never multiply by a negative number, right? Because then it flips the inequality over. But we can always be sure that these numbers are always positive. Why? That's obvious that that's positive, right? But n is always positive. So at least where we're looking, n is positive, right? So this will work. We can not worry about the flipping. All right, so let's multiply this out. Left side becomes n cubed plus 2n squared plus 5n. The right side becomes, let's see, n cubed plus 4n plus n squared plus 4. Let me turn my phone off, or my ringer real quick. Forgot to do that. So get some things to happen here. What do we have? Can get rid of this and this, bring it to the other side. I think I'm getting n squared plus n is greater than 4. Is that true? Not always, right? But eventually, is it true? I mean, like for n equals 1, is it true? No. For n equals 2, is it true? Yes. And then after that, is it obvious that it's true? So this is good for, or I'll say that's valid, for n equals or bigger than 1. Do you agree it's good? For n is bigger than 1? So the question is this test going to fail to work now? Because it had to be decreasing, right? That's what it said. And this is not always decreasing. It starts out, It increases and then it decreases, right? So, does it fail? And the answer is no. So what I want you to do is I want you to come up here to the integral test. I want you to add something on here. Okay, this is not this is a pretty standard sheet. You can just find this on the internet. So I just copied it a few semesters ago. I want you to add something that's not in here. On integral test, you see where it says that it has to be decreasing? Underneath that, put eventually, which means it doesn't always have to be going down. Your sequence can start, can be going up for a while, but eventually, after some point, it has to decrease and just keep decreasing. It can't start behaving bad again, all right? So this point where that happens could be, what, at 2, right? For us, it's at 2, it starts going down. But it could be at 100, it could be at 1,000,000. It just eventually has to. All right, so that's good. Now, let's compare that to doing it the other way. The other way is take the derivative of the function. So what is f prime of x? You'd have to use quotient rule, right? Because we have x over x squared plus 4. So use your quotient rule on this. However you do the quotient rule. I do derivative of the top times the bottom minus the derivative of the bottom times the top, all divided by the bottom squared. I think everyone does some variation of that, right? Let's clean it up a little bit. And so I'm getting 4 minus x squared over x squared plus 4 squared. Everybody got that? You take that derivative, okay? What am I trying to show? Is that this is eventually negative, right? That if the derivative is eventually negative, that means that the original function is eventually decreasing. And so, is this negative or not? Well, look at the denominator. What can you tell me about that denominator? It's always positive, so this is what we have. The bottom is always a positive number. And what about the top? 4 minus x squared. Well, remember, x can only be 1 or bigger. If I plug in 1, I'm going to get what? 4 minus 1 is going to be a positive number. That's not what I want. If I plug in 2, I'm going to get what? 0. Still, that's not a negative number, but if I plug in 3 and anything after 3, well, anything after 2 would work if you're on all real numbers. But do you see eventually that this is going to turn into a negative number as x gets bigger? So this will be negative up here if x is bigger than 2. Any number bigger than 2 that I square here will result in that top piece becoming a negative number. In both cases, I've shown that it's eventually decreasing. Okay. What's the next condition? It needs to be integrable. Is f of x equals x for x squared plus 4 integrable? And that just means, can you integrate it? Well, actually, technically, to say a function is integrable is a lot more than just can you integrate it. It has to do with whether or not it has a certain number of discontinuities. But for us, I mean, it really comes down to can you integrate it? Is it a function you feel comfortable integrating? Yeah, I hope so. So I'm going to just put check, it is. And so now we do the test. And the actual test that after we've met the conditions is this. Here it is. We do the integral from 1 to infinity. of x over x squared plus 4 dx. We make a basic substitution because the derivative of that is 2x dx. So half of du is x dx. I would trust everyone here could integrate this. So this integral turns into integral, I can pull out a 1/2. I believe I have 1 over u du in here. And what's the antiderivative of 1 over u? Natural log, so I have 1/2 natural log u plus a constant, right? But what is u? It's the x squared plus 4. So this is the antiderivative, right? That's the antiderivative. So I'm going to go back to this. This was all just my substitution just so I could find the antiderivative. Now let's go and figure out what this blue thing is, because we have a limit of integration that's infinite. So this is an improper integral. So the way we did this is we said this up here is going to become the limit as t goes to infinity of the integral 1 to t x over x squared plus 4 dx, which we just found to be, we got that antiderivative. I'll put it in brackets here. It was 1/2 natural log x squared plus 4, evaluating 1 to t. And what do we have? What happens when you plug in t and then let t go to infinity there? It goes to infinity, right? This thing, when I plug t in here and then let t go to infinity, I get natural log of infinity. It becomes infinite. And then who cares what I get when I plug in 1? I mean, it's just going to be a number. So this thing becomes infinite. Which means that the integral diverges. And this test says that if the integral diverges, what? The series diverges. I'm going to use implication symbols instead of arrows. We're done. So please keep in mind, well, were there any questions on this, the work here involved? Keep in mind that on a test, if you come to this problem and this is all of your work right here, this is the entire work for the problem, you got the correct answer, you're gonna lose points, right? Because even though you've applied the test properly, there's no indication that you actually confirm that you could use the test. And that's part of what you have to show. So I would be expecting to see, where'd it go? This sort of thing in here also. I hate taking off on tests for that, but I'm warning you, I'll continue to warn you, you have to be clear with your work. All right. Let's do another one. Would y'all like for me to let you try this one? Like get working on it or just show you? Come on. Y'all can talk to me. It's okay to talk. You want to just see it? All right. Well, if you're the one talking, then we'll just do what you want. All right? Yep. See, this is the worst kind of problem on a test, because this is a problem where a lot of people kind of know what they need to do, but then they can't do the integration. The integration gets them or something, and it's unfortunate because you know that you're supposed to attack it with a certain method, but you can't apply it properly because the other calculus is catching you. All right, let's run through this quickly. Nth term test. 1 over infinity, it's going to go to 0. It's going to be an inconclusive test, right? Test is going to fail. Next thing is not geometric. Harmonic, no, it's not linear in the denominator. Telescopic, I don't see how we're going to make subtractions out of that. I don't see it. Do you see how we could possibly make this turn into two things being subtracted? And so that really only leaves us with integral test. So do you see a way of integrating that? Yeah or no? U sub, I see this right here, natural log of n. I see its derivative. Its derivative is what, 1 over n? So I see a basic U sub here. So I'm thinking integral test. So integral test. Conditions. 1. What? Is it continuous? Is f of x, now watch, I'm converting it over right now. Continuous. Not everywhere, right? I mean, there's places where this function is completely undefined. It has a natural log in it, so it can't be defined for negative numbers or 0. And division right here by 0. So that you cannot plug in a 0 and you cannot plug in a negative number, right? But anything else would work. So is it continuous? Yes. On 1 infinity it is. And that's all I care about, right? It's actually continuous on 0 to infinity, but that's the only place I'm concerned with. So is it continuous there? Yes. Second thing, what is, what's the next thing? Is it positive? I'm just going to put this. Well, 1 over x, natural log x squared. Boy, that squared sure is nice, isn't it? That squared on the natural log means I don't even need to look at this, right? And 1 on top is always positive. So the only thing that's going to affect the sign of this thing is that x. So this will be greater than 0 if x is greater than 0, right? Which is true on on 1 infinity again. Third thing, is f decreasing? Now this is where you could do two different methods, right? I want to show you the first method because I want you to appreciate the other method now. Let's try and figure out if we can get control over this inequality. So we're going to rewrite the original sequence in here with n, and then we're going to replace n with n plus 1. I'll read that okay. You can multiply both sides here. Cross multiply. We don't have to worry about flipping the inequality. This is one thing I always wind up taking off on a test for, is that a student will write this line right here, this next one, and they'll just be like, yeah, sure, you know, that's obvious. I just don't think that that's obvious. I don't think that I think it's dangerous to think that that's obvious. Now, what you could do is you could try and expand all this out. You could take the n plus 1 and multiply it times this and distribute. But do you see that this is not a polynomial? So like with the polynomial that we've had up to this point, you could always like cancel some things out and then kind of get control over it. But the natural log function acts a little different, doesn't it, than a polynomial? So it's, I would hope, a little harder for you to convince yourself that this is going to be true. Is there anything you could do with this, like that natural log? Can you break it into two natural logs, or no? Because there's addition between them, right? Addition inside. You can only break it with multiplication. So you're kind of at a point here where maybe you could keep going algebraically, maybe not. Which would leave you with the other way, which would be to show that the derivative is negative. What's the derivative of this function? So let me write the function down here so I have it. Right, that was it. How would you like to take that derivative? Do you want to do quotient rule, or do you want to bring everything on the bottom up and then take the derivative? You can bring everything up first? I mean, you could rewrite the original function like this. Couldn't you? Bring the x up to the top, it's x to the negative 1. Bring natural log x squared up to the top, it's natural log x to the negative 2. And then from here, when you take a derivative, apply a product rule right here. Let's do that. So what is the derivative here using the product rule? Negative 1 x to the negative 2 times the second function. So all I did there was derivative of x to negative 1, then rewrote this next to it. Plus, because it's product rule, now the derivative of this one, which is chain rule, negative 2 comes out. Natural log x to the what? Negative 3. And then, am I done? Good, times 1 over x, which is derivative of the natural log part. And then am I done? X to negative 1 again, which is the first function. And what am I hoping for here? That this thing is, that the original function decreasing means that this derivative needs to be negative. I need to convince myself and you that this is always a negative expression. So let me clean it up. Any questions on this derivative? Or I'm taking all my negative exponents and dropping them down. This one already had an x in the denominator, so this one came and joined it. So here we go. Is this always negative or not? Tell me about this right here. It's always a positive number, right? Because they're both being squared. Negative 1 over a positive number. So you're going to have negative over positive, right? That's the first thing we have over there. Minus, and then over here, 2 over, so 2 is always positive over. Are these going to be, what can you tell me about these? X squared is always positive. Natural log of x is not always positive. You cube it, it's still not always positive. But remember what natural log of x does? right? Where is natural log of x 0? Where's natural log 0? At 1, right? And where are we looking? From 1 on, right? So to the right of 1 isn't natural log positive? Yes? So this will always be a positive number where we are concerned, right? So after 1, it's going to be positive. And so cubing, it's positive. So I can guarantee myself that this is always going to be positive as long as x was bigger than 1, right? If x was bigger than 1, this is what's going to happen. So you have a negative number, and you subtract from it a positive number. What can you tell me about that? That's always negative. So this is a negative number. Check, it's decreasing. Questions? All right. The fourth condition, integrable. Yes, because I'm about to integrate it. So here's the actual test. Integral 1 to infinity, 1 over x natural log x squared dx. It was 2, sorry, thank you. It was 2. Yeah, the original sum, right, was at 2? Yes, okay. So that's good because we wanted this to be decreasing. It's decreasing after 1, immediately after 1. We're not going to start till 2. Yeah, sum started at 2. Why is it not 1? Natural log of 1 is 0. You get division by 0. The series wouldn't even be defined when the first thing you try and plug in. So, all right. I don't really feel like going through that integration. Yeah. I think you could probably do that integration on your own. Yes. I'll just set it up. What would u be? ln x. And you've got du right there. All right, I'll do it. Du is 1 over x dx, right? Which you have there. So that integral turns into integral 1 over u squared du. This is u squared. 1 over x dx is du exactly. We're not even off by a constant. So you get direct replacement there. This is integral u to the negative 2 du. Antiderivative of u to the negative 2 is negative u to the negative 1, which for us means, let's see, negative 1 over, what was u? Natural log x. So I just drop the u back down to the denominator, which is here, and I replace u with natural log x. This is our antiderivative. So now we come back to the integral, and I'm supposed to write what, limit and all that stuff now? But, you know, we get to a point where we've done enough of it that we don't have to write limit each time. You can actually just write this. Watch me. I'm going to write the antiderivative. I even saw some of you on your test did this, which means you know what I'm talking about. You've seen it kind of before. We just do the integral, the limits of integration 2 to infinity. And we realize that what we mean by infinity is that we're going to take a limit. We're going to let this x get bigger and bigger and bigger. And if it turns out we need L'Hopital's rule or something like that, we can go on the side and do that, but just we should be able to evaluate this just by inspection. What happens if I let this x go to infinity? Natural log of infinity is going to become infinite. Negative 1 over an infinite number is going to 0. So that actually goes to a nice number, right? So when we plug in infinity, we get 0. Then minus, now we plug in what? 2. Natural log of 2 is a number. Negative 1 over that is a number, right? This is a number. Do I care what it is? Absolutely not, because all I care about is whether or not this integral converges or diverges. And from this, it's going to converge, isn't it? I've got a number. So this all equals a number, which implies that the integral, right, 2 to infinity of 1 over x natural log x squared dx converges, which implies the sum n equals 2 to infinity of 1 over n natural log n squared converges. All right. And that's it. We're done. All right. We are supposed to take a little break here. Before we take the break, this will take 5 minutes to do. It's not going to take us a long time. I'll show you what's called a P-series. A P-series is very much like harmonic. Remember with harmonic, we just said, hey, constant over linear, done. P-series is very much like that. P-series, all P-series look like this. Sum n equals 1 to infinity of 1 over n to the p. If p is greater than 1, the series, is this on your sheet? Yes, okay. The series diverges. And then if, I'm not going to write anymore, it's right here. Converges, sorry, converges. And if p is less than or equal to 1, it diverges. And it says on the comments on the side here that this is very useful for comparison tests, which we are going to do after our break. But just to make sure we understand how this thing works, p less than or equal to 1, the series diverges. That's in your notes, or in your handout there. So look at this one right here. As an example, does this converge or diverge? You tell me. 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus ... So you have to first be able to come up with a formula. What do you think? Converge? So what is the formula for this? What is the actual series? 1 over n squared. 1 over n squared. So you start with 1, right? 1 squared is 1. You get 1 over 1. That's 1. Then you go to 2, right? 2 squared is 4. So you have to recognize that all of these denominators are squares, perfect squares. 2 squared, 3 squared, 4 squared, 5 squared. Be careful because that is very different than this series. Let's say 2, 4, 8. What series is that? What type is this? 2 to the n. That's a geometric series, right? This is 2 squared, 2 cubed, 2 to the 2 squared, 2 cubed, 2 to the first, 2 to the fourth, right? Here, with the geometric series, the thing that's changing, right, the index is the exponent. With the P series, it's the actual base itself that's changing. The power always remains the same. So just be careful not to confuse the two. So we look at this and we'd say, this right here, all you have to say is this, P series, right? n is, or not n, p is 2, which is greater than 1. And what is it? What is the condition, or what is the conclusion if p is greater than 1? Therefore, it converges. No work. This one will be so obvious. Hopefully it'll be obvious. Does that converge or diverge? That one diverges. And it's a p-series again. You have to recognize that this is sum n equals 1 to infinity, 1 over n, or 1 over what? What is that? N to the 1/2, which is square root of n. So the first one is 1 over square root of 1, square root of 2, 1 over square root of 3, 1 over square root of 4 is 2, square root of 5, square root of 6. So this is a p-series with p being 1/2, which is less than 1, which it means what? Divergent. Now, I'm not proving this. If this wasn't a summer course and we had more time and we didn't get that holiday on July 2nd or whatever it was, then I would actually go through and prove this. We're just going to take it on faith. I don't like doing that, but we will. If you're really interested, I've got some other videos from previous semesters where I've done the proof of that. So you can go watch it if you want. Just curious real quick. I know we are taking a break. I'm right at 10:15. When are we supposed to take our break, though? Like, don't I usually go to like 10:40? Yeah. I think it, but I feel like a break. Don't you all feel like a break already? Y'all look like y'all need a break. What about this one? Sum n equals 1 to infinity, 1 over n. That's 1 plus 1/2 plus 1/3 plus 1/4. Do you recognize this? What series was that? Well, we did this last class. What series was that? Harmonic. We said all harmonics diverge, didn't we? Yes? I want you to realize now that a harmonic series is a p-series. The p is actually what? 1. Right? So if you look at the set of all series that are p-series, so those are all the p-series that exist out there, then inside there's one particular one. It's the harmonic one. Right? The harmonic, harmonic is in there. So it's like a subset of all p-series. It's just one simple case. Like a square is a rectangle, right? Same sort of thing. Harmonic series is a p-series. So this is p-series. You could say, so on a test, you could say one of two things here. You could say, this is a p-series p1, therefore it diverges, or you could say harmonic diverges, either way. Okay? Let's take a break. Let's say about, I don't know, 10:30. We'll take an extra long break since we're going to have a longer stretch here in a second. Your tests are up here if you haven't picked them up. All right, moving on to the comparison test. All right. As the test states, it is something that we use, and we are going to do a comparison in order to figure out whether or not a series converges or diverges. So we will want to know, if some series converges or diverges, right? That's what we want to know. So we look at a series which is different than the one we're trying to figure out. So this is A sub n, I'm calling this B sub n. We're going to compare it to another series. Of which we do know its behavior. That doesn't make a lot of sense, but in other words, we know if it converges or diverges. So we got this series, we're trying to figure out what the heck it does. So we compare it to this other series that we do know what it does. We do know it's convergent, or we do know it's divergent. Then here's kind of our conclusion. Suppose, and before I forget this, I need to add one thing up here. Both of these they're both greater than 0. Oh. In other words, this test won't work if our series is ever negative. That's called an alternating series, right? Because our signs change. We have a different test for that, and it's actually a really nice test. It works pretty clean. So this is only when we're comparing series that have positive terms. Did I show y'all what this S means? Suppose, that's what that means. Suppose the B sub n one converges. And the sequence A sub n is less than B sub n eventually. What do you think the conclusion will be? A sub n has to converge. The series. I mean, it's a pretty simple idea if you think about it. You're trying to figure out what A sub n's doing. You try and find a series that's always bigger than it, right? A series that every term is always bigger than the A sub n. So in terms of a picture, it looks like this. Let's say A sub n is here in black. You're trying to figure out what this is doing, right? But then you come up with this B sub n. I'll say this is A sub n. You come up with this B sub n that's always bigger than it, right? Always on top of it. That's your B sub n. And you actually know from the beginning that this B sub n had to converge. Well, if adding up all the blue ones is a finite number, then adding up all the black ones has to be smaller than that. It must also be finite. So it's a pretty simple idea. We just need to make sure we get the inequality correct. B sub n converges, our A sub n's are smaller than it, then it converges. What do you think the other thing that could happen would be? Suppose the B sub n diverges, right? And our A sub n's are bigger than or equal to the B sub n's, eventually. You all know what I mean by eventually now? Then diverges. Oops. So that's the opposite of this picture. It would be like the A sub n's are on top of the B sub n's, and the A sub n, sorry, the B sub n, the one that's below, blows up to infinity. Then the blues are always bigger. That has to blow up to infinity also. Did I put less than or equal to? Change this to an equal right here. Sorry. Right up there. All right, let's see. Actually, I'm going to do our first example. Does this converge? I'm just going to put CD question mark. You understand what I'm asking? Does it converge or diverge? We did this problem a little while ago, right? We did the integral test. So let's see if there's possibly another way of determining the same thing that would have been even easier than what we did before. In the long-term behavior of this, as n gets very large, this 4 really doesn't play a role, does it? It really doesn't factor into it much, you know, when these n's are huge. So this thing behaves a lot like just n over n squared, doesn't it? Doesn't it really behave like n over n squared? I'm wondering maybe if we can compare it to this series, n over n squared. Now, what is n over n squared? It's 1 over n, right? And that's a series I know about, don't I? What type of series is this? It's harmonic. Or P series, with P being 1. In either case, it diverges. Now, this may work, it may not. But does everyone agree, at least, that this thing looks a whole hell of a lot like this? Yes? In the big behavior at the end of it, like further out you go. All right, so I'm going to try and compare this series to a harmonic series. And this harmonic series diverges. So go back to what I said here. Suppose B sub n, that's the one we're comparing it to. Suppose it diverges, which is what ours does, right? I need to make sure that this inequality is true. That the A sub n is always smaller than the B sub n. Or, sorry, bigger than the B sub n, yes? If that's true, then I can conclude that mine must diverge, the one that we're interested in must diverge also. Let's see. So I'm going to put here now, I want to show, and we like to show a lot of things in math, so a lot of times we don't write want to show, we write WTS. Want to show that A sub n is greater than or equal to B sub n. What's A sub n? Make sure you understand which of these is which. The original one, that's this one up here. That's the one I'm going to be trying to figure out. That's A sub n. What's B sub n? 1 over n. This is B sub n. Now, for the comparison test to work, we have to make sure that both of these were positive. Are these both positive? Yes? Okay, so I want to show that this is true, and A sub n is bigger than 0, B sub n is bigger than 0, so I can use the test. And I'm just going to do check marks next to those. Those are done by, I just did those by inspection, just by looking at them. It's clear that those are always positive, going to give me positive terms. But this inequality I have to show. So let's write down A sub n, n over n squared plus 4. Is that bigger than or equal to 1 over n? Question mark. If it is, I can draw my conclusion, can't I? What happens though, let's see, we do kind of like a cross multiply thing. N squared is greater than or equal to n squared plus 4. And then you subtract n squared on both sides, you get 0 is greater than or equal to 4. Is that true? No. Fail. But that means that, not that this whole test fails, it means what I compared it to doesn't tell us anything. Sometimes I'll see students, they'll draw the wrong conclusion here, is that they'll say, all right, I went to compare it with this. This one diverged. Since this one diverged, I tried to show this was true. Since it wasn't true, mine must do the opposite of what this one does. That's not the case. We already know what this does, don't we? It diverged, didn't it? But this comparison, our choice of our comparison wasn't good enough to give us any conclusion. Understand? So I'm going to need to try something else to compare it to. So let's take a look back here. What was the problem with this? These ends canceled. That was fine, right? And if I would have had like an n plus 5 over here, n squared plus 5, wouldn't have this worked? So how could I make this n squared plus 5, or could I do an n squared plus 5, or somehow, how can we make this side bigger is what I'm getting at. Could I do anything to make it bigger? You wanted to compare it instead of 1 over n to 1 over n plus 5? So that would make this an n plus 5 here, wouldn't it? And then when I multiply, cross multiply, this side would become what? N squared plus 5n. And the n squareds would still cancel. And you would get, what, 5n is bigger than 4 or something like that? And that would be true eventually? Yes? So look, in my actual crash and burn in this, I've actually kind of given myself insight into what I should try by trying to make the inequality work. So it's looking like n plus 5 would work, but do you know what n plus 5 work? What it does? What does 1 over n plus 5 do? That's harmonic, right? Constant over linear? That's harmonic, it diverges too. So that should work. Do you understand this thinking here? So I'm going to say, haha. Use, go ahead, what? No. Square root, where? This right here. Yes. I multiply this times 1. Got this. This times n. Got this. Like a cross multiply. Okay, so here we go. I start over. All right? I'm going to compare to sum 1 over n plus 5. This is harmonic. Therefore, it diverges. So I want to show that my a sub n is bigger than or equal to the b sub n. I'm not going to put that the a sub n and b sub n's are bigger than 0 because, well, okay, I'll put it. And a sub n, b sub n are bigger than 0. Those are both still true, right? Those are both true still? All right, let's try and show this inequality. I need to show that that's true in order to use this comparison test. So our a sub n hasn't changed, has it? Still n over n squared plus 4. Our b sub n is now 1 over n plus 5. Do your cross multiplication. N squared plus 5n is bigger than or equal to n squared plus 4. And that gives you 5n is bigger than or equal to 4. Is that true? Always, right? Well, for the n's we're looking at, true. Which means what? What does this mean to us now? Therefore, our series, right? Our series does the same thing that the one we compared it to does, which is what? It diverges. So which one of these was more work? The integral test or this? What do you think? I mean, just what's your feeling on it? Was more work? Yeah, probably. Let's do another. I'm going to let, well, I want y'all, there's a work on some of these on your own just because I want to see what y'all do, but all right, how about this? Converge or diverge? Sum n equals 1 to infinity, 1 over 3 to the n plus n. I am going to let you work through this one, just to get started. So on this one, again, let's look at what the long-term behavior would be. If n got very big, the 3 to the n would overpower the n, wouldn't it? I mean, n gets big also, but 3 to the n gets big a lot faster. So I'm thinking that the 1 over 3 to the n might be a better candidate, but we need to know what 1 over 3 to the n does. But this is the same as 1/3 to the n, isn't it? And even though it doesn't look perfectly like geometric, because remember on geometric you have to have like n minus 1 up here, we could get it to look geometric, couldn't we? And eventually when we did it, we would what? Subtract and add 1 up there and do all that. The r would still be the same, wouldn't it? The r would still be what? 1/3, wouldn't it? So with this, I would have geometric series with r being 1/3, which is less than 1, which means it would converge, right? So I'm going to compare this series with a convergent geometric series. And since I'm trying to show convergence, go back to the notes. The test says if the series I'm comparing it to converges, I have to show this inequality is true, not the other one. So I want to show, yes. My what? Well, no, because I would have to do -1 plus 1, and that would pop a 1/3 out. The r should stay the same though, unless this was like 2n and then it would change it, but it's not. It's n. So I won't need a in order to still say it converges. So I want to show that my a sub n is always less than or equal to my b sub n, and I need to make sure that the a sub n and the b sub n were bigger than 0. Were they both bigger than 0? Yes. So we're working with positive series here. Now let's write down the comparison. 1 over 3 to the n times n, that's a sub n. I need to show it's less than or equal to 1 over 3 to the n. You could almost just say it right here, because these almost have the same denominator, right? The only difference is that I'm adding an n here, which makes this denominator bigger than this denominator. Same numerators. So if you're a little bit bigger on the bottom, it's going to make the fraction a little smaller, so this should be true. But if you do the cross multiply thing, you get the same conclusion. The 3 to the n's cancel on both sides, you get 0. N is bigger than or equal to 0. That's always true. So the inequality that I wanted to show holds, doesn't it? Which means this test worked, and I can draw my conclusion. Therefore, my original series will do exactly the same thing as the one I compared it to, which means it converges. Done. I'm going to set another one up, but I'm not going to go through the work. Converge or diverge? Sum n equals 1 to infinity, 10 over 7n cubed plus n squared plus n. The long-term behavior, as n gets big, the n squared plus n on the bottom aren't really going to factor in when n's big enough. I mean, we'd have to get to really big n's for these to be insignificant. But again, this would overpower these two. So really, this looks a lot like what? Maybe I compare it to imagine the n squared and the n weren't there. It'd be something like 10 over 7n squared. Oh, sorry, cubed, which is same as 10 over 7 Since 10/7 is a constant, I can pull it out. Do you know what this series does right here? Yes? What type of series is that? P series. P is 3, which is bigger than 1. It converges. So I'm going to compare my series to a convergent P series. So I want to show what inequality? Yep, A sub n is less than or equal to B sub n. Also, my A sub n was positive, yes. My B sub n was positive, yes. So I want to show that 10 over 7n cubed plus n squared plus n is less than or equal to which one? What do I work with here? What's my B sub n? So you have to be a little careful here, because if you do 1 over n cubed, if you do, you're actually going to have some trouble here. The 10/7 is actually going to be needed for us to see it easily. So just compare it to 10 over 7n cubed. That'll make things cancel real nice when you multiply both sides. You'll get a 70n cubed on both sides, right? Which will go away. And I told you I was just going to set it up. I may as well take it the whole way here. Is that true? Yep, it's true. Therefore, the original series does the same thing. Next test. called the limit comparison. It's the same thing that we just did, okay? We have a series with a sub n bigger than 0. We compare to a series and we know what this one does. So exactly the same as the comparison test. This is different though. It's called the limit comparison test. You start the same way though. But instead of showing the inequality that we had to show in the last one, here's what we do. If the limit as n goes to infinity of a sub n over b sub n equals some constant which is greater than 0 and finite, then the conclusion is this. Then whatever b sub n does, the series of a sub n does the same. A lot of times this is a preferred method over the comparison test because it just involves a limit and you just have to show that that limit is a number. And it can't be, this limit cannot turn out to be infinity. If it's infinity, this fails. All right? So let's see this on an example. Let's try this one again. See what happens. We've done this with the integral test. We've done this with the comparison test. Now we're going to use the limit comparison test to see if we can come up with the same conclusion. What do we want to compare it to? You want to try 1 over n? Because we said that that behaves over there a lot like 1 over n, doesn't it? When n gets big, the 4 doesn't matter. It looks like n over n squared, which is really like 1 over n. So I'm going to compare it to this, which is a divergent harmonic series, right? This is divergent. Also keep in mind, both of these are positive, right? 1 over n over n squared plus, so I can use the limit comparison test. So here's the setup of the test. I'm going to take the limit as n goes to infinity of n over n squared plus 4 over what? 1 over n. Now, that's a fraction over a fraction. Just flip it. Doesn't it become n squared over n squared plus 4? What's that limit? When you go top and bottom, isn't it, what, infinity over infinity? So L'Hopital, do L'Hopital once on this. You get what, 2n over 2n, which is just what? 1. Is that a constant bigger than 0 and finite? Yes. Since that is a constant that's bigger than 0 and finite, your conclusion is that whatever the b sub n did, that's what the a sub n does. What did our B sub n do? Diverged. Our A sub n is going to do the same thing. So therefore, sum this diverges. Well, I think we just sold ourselves on the limit comparison test, didn't we? I mean, compared to the integral test, this is way better. But that's not to say that the limit comparison test would always save us. It's just when we're looking at problems now, we want to start to really open up our view of things and not be narrowed down on one thing. Like, just because we can integrate the inside of this, just because we look at that and say, oh yeah, that's basic U sub, I can do that, I don't want to be fixated on integral test. I want to realize there's other tests out there that might work even better and faster. So think about on a test, time is an issue, right? And you're sitting there and you're doing this test, and one person does integral test, the other person does the limit comparison test. Limit comparison test student's done in about 5 minutes. Integral test person's there for 20, 25 minutes doing the problem, right? So there's a big difference here. And that is part of what's being tested, is that are you just going through the list one by one, or are you actually looking, thinking, this is the most efficient way to do it. All right. Converge or diverge? Sum n equals 1 to infinity n plus 5 over the cube root of n to the 7th plus n cubed. I think it's safe to say we would not want to integrate that, right? We wouldn't even think integral test. So, and I'm also going through nth term test would be the first thing I'd want to do on this, nth term. I mean, just look at the inside of that, let n go to infinity. If you did that, you'd realize it's going to go to 0 and it's inconclusive. It's not geometric, it's not harmonic, it's not telescopic. Integral, no way. Comparison, well, I just need to figure out what I'm going to compare it to. I'm thinking when n gets really, really big, right, it's really, the numerator is going to behave like n, and the denominator is really going to behave like this guy, right, but cube rooted. So n to the 7/3 is what this one looks like. This whole denominator looks like n to the 7/3 when n is large, and the numerator looks like just n. So I'm just going to take a swing at this. I'm going to compare this to n over n to the 7/3. Yes, and I'm going to clean it up. I just want to make sure everyone understood where the next piece is going to come from. This is going to be, what? 1 over n to the 4/3. What type of series is that? P series? It's convergent, because P is 4/3, which is bigger than 1, so it's convergent. So we have a convergent P series that we're going to compare to this nasty thing. Now, I could do one of two ways. I could do it with the comparison test or the limit comparison test. And since we've only done one example of limit comparison, let's try that one because it worked really nice last time, right? Would you agree? It worked really nice? Also, think about the inequality. If you did it with just the comparison test, wouldn't you have to set up an inequality right now? And look at what your A sub n is. Do you want to set this up with an inequality with this? I mean, that's going to be a disaster when you cross multiply. It's going to be, you know, how are you going to simplify this thing? It's a mess because it's got addition between it, so you can't just split it up. It's not looking like the preferred way. So I'm going to do it by setting up a limit. Limit n goes to infinity. I put the a sub n first, which was n plus 5 over, now this is still ugly too, don't get me wrong. Over 1 over n to the 4/3. Flip it. Bring the n to the 4/3 up and multiply each of these by n to the 4/3. So you get n to the 7/3 plus 5n to the 4/3 over the cube root of n to the 7th plus n to the 3rd. Y'all okay with that? Just bringing this guy up here and distributing through to those two terms. Now right now, if you just let n go to infinity, you're going to get infinity over infinity. Right? This is infinite, this is infinite. You may think L'Hopital's rule here, but I sure as hell don't want to take the derivative of this because that's going to be chain rule. It's going to be a disaster. This would be easy to take derivative of. So I'm going to do something. It was another approach that we used when we had infinity over infinity, which did not require L'Hopital's rule. And that was to try and get the highest power in the denominator to become a 1. Do y'all remember doing something like that? So I look at this n to the 7th. What I want to do is I want to divide this by n to the 7th so that it turns into a 1. But the only way to do it is to come in with something on the outside, top and bottom. Same thing, like a hidden 1 here. And so the one I'm going to choose to use should be what? How about this? The cube root of 1 over n to the 7th. Now, we'll talk about why it's this in a second. Why did I put 1 over n to the 7th? Because when I hit this with 1 over n to the 7th, it's going to divide it, and it's going to become a 1, isn't it? But why did I put it in a cube root? That's the only way I can put these two together, right? I have two cube roots. I can put two cube roots together into a single cube root. So that's why I couldn't just put 1 over n to the 7th, because pushing it in here would not be as clean. Putting it under the cube root allows me to pass it through. So let me just do, I'm going to leave the top alone for right now. I'll come back to it. Well, you know, I'll do this on the top. All right, so I rewrote 1 over n to the 7th cube root as what? Cube root on top. Cube root of 1 is what? Cube root of 1 is 1, right? Cube root of 1 is 1. Okay. And then the cube root of n to the 7th is the same as n to the 7/3. So this is just rewriting this thing with rational exponents. On the bottom, on the other hand, I pushed this in here, made it all one cube root, and it's just waiting to get distributed through to each one. And now let's distribute the top through and the bottom through, and let's see what we get. Limit n goes to infinity. On the top, when we pass this through, it cancels out, right? It becomes a 1. When we pass here to here, I'm going to get plus 5 over, what's 4/3 take away 7/3? Negative 3/3, which is negative 1. So this is going to be a 5 over n here. And then on the bottom, cube root of passing this one through here and here. What do we get? 1 plus 1 over n to the 4th. Now the whole reason we do this is to try and overcome this infinity over infinity thing. And by doing it like this, watch what happens when n goes to infinity. This one right here goes to what? 0. This one right here goes to 0. And the only thing left is 1 on top over the cube root of 1 on the bottom, which is just 1. Which is finite, right, and positive. Which means what? It converges. The original series, this nasty thing, does exactly what I compared it to, and what I compared it to converged. And we move on. Are we getting through this list? Where are we at? Ratio root. So notice in this table, comparison, it lumps the comparison test together. So when you look in here in comparison, right there in the center, it says part I, if B sub n converges, if the series B sub n converges, and the inequality holds, then the A sub n converges. If the B sub n diverges and that inequality holds, then the A sub n diverges. And then the part 3 is the limit comparison. Part 3 says if you take the limit and you get a C, and it's a positive real number, then both series converge. Make sure on that C, you're aware, you can put a little note there if you want, C has to be finite. In other words, if you take this limit and you get infinity, the test fails. All right, so what we're going to do next, I know ratio and root test look like they're next in line, but we're actually going to do the alternating series test next. So the alternating series, as you might expect, is something that you use when you have a series that looks like this. Something in here, doesn't matter what it is. And what you're getting is like minus something, plus something, minus something, plus something. So you're alternating, right? Minus, plus, minus, plus, minus, plus. Or you could have it the other way around, where you're getting something like a positive, then minus, positive, then minus, positive, and minus. And do you remember, we can always make a series alternate by using the negative 1 to the n thing? Negative 1 to the n plus 1, or negative 1 to the n, and that'll make it alternate. So we have not done any series that alternate yet, right? To try and figure out if they converge or diverge. Now we're gonna deal with that. So here's what the test says. Suppose we have a series and we've got this negative 1 to the n or n plus 1. In fact, it really doesn't matter if it's n or n plus 1, or it could be n plus 2 or n plus 3. We have the part of it, this part right here, is the part that makes it alternate. And you remember when I would give you a sequence and I would say come up with a formula, you would always use something there to make it alternate, and then everything else you would have to figure out, wouldn't you? Everything else? That other piece that you would have to figure out, we're going to call that A sub n. So the distinction here is that in the past, A sub n has always been everything that's there, right? The whole thing. Now the A sub n is the part that's not the alternating part. It's all the other junk. Okay, so suppose we have this, and that would mean that the A sub n that we have there would have to be positive. This piece was positive. This part's the alternating part. Then if 1, A sub n is bigger than or equal to A sub n plus 1, and 2, the limit as n goes to infinity of A sub n equals 0, then the series converges. And on this part 1 here, you can put eventually. The alternating series test is very easy to apply, because let's take a look at what you have to do to show it. What is part 1 saying? You have to show that the sequence, right, is doing what? Decreasing. And then what is this? That's the nth term test. It's the first test we ever learned. If that was 0 in the past, what did we say? We don't know anything, right? The test failed. But if it's an alternating series, this actually does tell us something, but we need one other condition to be met. We need it to be decreasing. If it's decreasing and the nth term test gives you 0, then you can say it converges. That's the test. That's it. So let's see it in play. Classic example here. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus dot, dot, dot. What does that series look like? What series is that similar to? We've seen this before, but not with the minus in there. That looks like 1 over n, doesn't it? That looks like a harmonic series. What do harmonic series do? They diverge. But see, this is not a harmonic. This is what we consider to be an alternating harmonic. But at the end of the day, it's an alternating series. So let's generate a formula for this. The formula would be n equals 1 to infinity. Okay, I need to start with a positive number. So how about negative 1 to the n plus 1? That'll work. And then the rest of it is just what? 1 over n. That should create that series, shouldn't it? The 1 over n is the harmonic part of it, and then the alternating part is that negative 1 to the n plus 1. So since this is an alternating series, I'm going to use the alternating series test. I just want to make sure that we all understand I'm going to call this piece the A sub n. This part does not come into it at all for the test. I'm going to let everyone know what I'm about to do. If you want to put AST for short, or that's fine. The first thing I have to show is that A sub n is less than or greater than or equal to A sub n plus 1 eventually. This is going to be super easy to show. Right? This is 1 over n is greater than or equal to 1 over n plus 1, which means n plus 1 is greater than or equal to n, which means 1 is greater than 0, and that checks. So the first part was clean. The second part is even cleaner. We're taking the limit as n goes to infinity of A sub n, which for us is 1 over n. And where does that go to? 0. And that's what I needed for the test to give me a conclusion, right? So both conditions were met. It was decreasing, and the nth term test gave us 0, and therefore the conclusion is what? It converges. It's interesting, I guess. A harmonic series diverges, but an alternating harmonic series converges. Don't know what it converges to, but it converges. It's a little bit of work to try and figure out what these things converge to. Let's see if I can find something here real quick. Spring 2015. I don't know if I have this here or not. Forget it. All right, this is a good example here. Converge or diverge? I'm going to work through this one and show you a little bit of a dangerous situation, all right, on purpose. You see an alternating series, right? -1 to the n automatically. Everything that we've done, right, comparison test, limit comparison test, always required that our A sub n inside be positive. And so all those tests you throw out the window. The only thing we really have is alternating series test. So you sit there and go, oh, I'm going right to it, right? Alternating series test. What's the A sub n for us? 3n over 4n minus 1. And so you have to show two things, don't you? A sub n greater than or equal to A sub n plus 1. Second thing you have to show is the limit as n goes to infinity of a sub n equals 0. That's the two things you have to show, right? If those two things are true, this thing converges. I'm going to do the second one first because we're going to see something happen here. What is that limit? Three-fourths? Because you get infinity over infinity. So you do L'Hopital once, you get 3/4. That is not equal to 0, right? That is not equal to 0. What does that mean? That's what I want to make sure everyone is clear about. What does that mean? What can we say? Can we say it diverges? Did we meet the conditions of the test? The test failed. That's it. That's all you can say. The test failed. So that's one of the tricky places, is that if this test tells you if it converges, right? That's all this test tells you, is if it converges. Then if the test fails, that does not mean that it diverges. It's like the first thing I can think of, a pregnancy test, right? Take a pregnancy test, it fails, right? Does that mean you're not pregnant? Hopefully not, right? You know what I'm saying? I mean, just because the test fails does not mean that you can conclude the opposite of that. You could have a false negative, right? I don't know if that's a good enough analogy, but the test is there to try and determine, in this case, convergence. The failure of the test does not mean divergence. It just means that you don't know if it converges or diverges. So this test fails. We have no other method, do we? Like we haven't looked at anything else. So how are we going to tell? Well, again, I told you I was going to work through this on purpose, kind of the wrong way. What's the first thing we're usually supposed to do? Nth term. And when you do an nth term test, what you can see happening here is that as you let n go to infinity, what happens to this? Just back and forth, plus or minus. And what are these? What happens to 3n over 4n minus 1? It's getting closer to 3/4, isn't it? So you have like something that's getting close to positive 3/4. The next one's going to be getting close to negative 3/4. Then positive 3/4. Then negative 3/4. Then positive 3/4. You know what I'm saying? So if you were to plot this sequence, here's 3/4 up here. Here's negative 3/4 down here. Your sequence, who cares what it's doing in here? But I know that towards the ends, it's like up here, and then it's down here, and then it gets closer up there, and then closer down here. Is there any way that can converge? No way. No way. You need this thing, right, to go to 0 for it to converge. This thing is not going to 0. So by the nth term test, the limit as n goes to infinity of the whole damn thing is definitely not 0. And the nth term test says if that's not 0, it's what? It's divergent. So this means we have a divergence. What I'm saying is you didn't have to do alternating series test. If you just would have remembered to do nth term test first, you would have concluded that it was a divergent series. But I wanted you to see an example of the alternating series test failing and making sure you're drawing the right conclusion. It turns out that, yes, it was divergent, but it wasn't divergent because of this. It was divergent because of the nth term test. Test fails. All right. Still hanging in there? square root, sorry. So because of what I just said, we probably want to do nth term test first here. And if you did nth term test, it would fail. It would be inconclusive. All right, so let's just say we've done that already. The only other thing we have is that it's an alternating series, so we do the alternating series test. First condition, I need to show that a sub n is greater than a sub n plus 1. The second condition that needs to be met is that the limit as n goes to infinity of what part? What's our a sub n? Yeah, it's just this piece right there, right? So n over square root of n cubed plus 2. Well, I need to show that that's 0, right? Take that, if it's 0 and then this holds, then I can say it converges. How about the limit? You want to do the limit first? Okay, we can do the limit first. I would multiply the top and bottom here. Well, I'll do it on the outside, it's easier. I'll do 1 over the square root of n cubed. 1 over the square root of n cubed. You don't have to put the square root on the bottom. You could do the square root on the whole thing, couldn't you? I put it on the bottom because square root of 1 is what? 1. So it didn't matter if it was on the top. Either way, remember I'm picking out the n cubed. I say I want to kill that off. So I need divide by n cubed, and then I throw a square root around it so I can put them together. Up here I can't really do much of anything but, you know, leave it and pass it through. So limit n goes to infinity. Let's do the bottom. I'll just come back for the top. Square root. That 1 over n cubed is inside here with this one. So when it passes through, it's going to make that a 1. What's it going to make this? 2 over n cubed. Good. Okay. On top, you might want to rewrite this. I would do it like 1 over n to the 3 halves. That's the way I would have rewritten this. That way when I multiply that times the n, you wind up just getting 1 over n to the half. These are just properties of exponents, right? That's all this is? Properties of exponents. What is this limit? 0. Is that good or bad? That's good. For the alternating series test, that's what we needed, right? This guy goes to 0. This guy goes to 0. 0 over 1. 0 over 1 is 0. So we're good. This part is the part that's going to suck. Because you would have to show that what n over the square root of n cubed plus 2 is bigger than or equal to n plus 1 over the square root of n plus 1 cubed plus 2. Does that look like something you want to do? Probably not. What's the alternative to showing decreasing this way? Derivative. We can again kind of view this as a function of x and show that the derivative of it is always negative. If we can do that, then we can show it's the same thing as showing decreasing this way. So I'm going to kind of go, nah. I'm going to look at f of x as being x over square root of x cubed plus 2, and I want to show that f prime is negative. Understand? That'll take care of my decreasing if I can show that. What is the derivative here? You want to do quotient rule? Derivative of the top is 1 times the bottom minus the derivative of the bottom. Oh, great. That's chain rule, isn't it? Derivative of the square root of something is 1 over 2 times the square root of that something. Chain rule says now to take derivative of what was inside, which is 3x squared. And then don't forget to hit it with what the numerator was, which was x. And then take this whole thing and divide it by, what, the denominator squared? X cubed plus 2. And remember, we're looking at x's bigger than 1 and on, right? 1 and on. Oh, man. The problem here is that we have subtraction, okay? We have a positive number here, guaranteed, yes? And we're taking away whatever this is. What is this, though? This is positive number, right? Positive number, positive number. So you have a positive number minus a positive number. You can never tell if that's going to be negative, right? Positive minus positive. That could be 5 minus 3. It could be 3 minus 5. So you actually need to figure out in some way the magnitude of what's happening here. The magnitude of each of these values. Does the denominator matter? This is a positive number, isn't it? So that's not going to affect the sign. If the top's negative, it's going to stay negative. If the top's positive, it's going to stay positive. So let's look at the top. Try and come to grips with this. Just the top. What do you think we should do to try and figure out what's happening here? Well, can't do it. It's just an expression, so I can't do that. But what should I do to try and figure out if this is a positive or negative number? Common denominator. Put them together. Turn it into a ratio. Maybe that'll help. So I need to look at this first one like this. I could do this. It's not wrong to do this. Pushing them together, this one, I'm going to have to multiply the top and bottom here by this, right? So when I hit the top with this, the two roots come together, the root goes away, and we have a 2 in front of it. So a 2, and then we have the x cubed plus 2. Then over here we had minus 3x cubed, and then over here on the bottom we have the common denominator. Is that common denominator going to matter anymore? No, because the common denominator is always going to be positive number. So now we're reduced to just looking at the top. If I distribute through, I get 2x cubed plus 4 minus x cubed. No, 3x cubed, sorry. That's my top, which is just 4 minus x cubed. Is that negative? Eventually. This is less than 0 when x is what? Greater than 1? Well, if x is a real number, we would have to actually figure out, cube root of 4 or something like that is when it would start happening. But for us, we don't care, right? 1 and on, at 1 it doesn't work. But at 2 it works? Yes? Okay. So eventually this will be a negative number, and that means eventually the function is decreasing, which means eventually the sequence is decreasing, which means we can draw our conclusion. Decreasing sequence eventually, and The end term test on just the positive part of this series went to 0. Conclusion, original series converges. Yes. All right, all right. I have some homework. We're not done, sorry. We still got a ways to go here. Got 30 minutes still. Especially when you're having fun, right? All right, so for homework, page 443, 7 through 28, page 453, 6 through 30. There goes your weekend. We're almost done with this class, though, right? What do we have, like 2 more weeks or something? 3? I don't remember when the last day is. July 30th? July 30th? Yeah. We meet 1, 2, 3 more times, and then we have a final. I don't know what we're going to do. Yeah, I don't know. Well, remember how we've been splitting it up where we have the test and then lecture. So it's equivalent right now. We have the equivalent of like 4, 5, 6 lectures, like a traditional semester, like 6 lectures left, 3 weeks, but we're doing that in 3 days, right? Which is what summer's all about. All right, so that's a lot of work right there. But that's, at least it's broken up into sections. So my advice to you is this, though. On a test, I would never direct you to use a particular test. I would never say, use the integral test to do this. So in your homework, if you're doing a problem like the n over n squared plus 4 that we did 3 different ways, 4 different ways? How many? I don't know how many ways we did it. But if you were looking at that problem in the homework and it tells you integral test, ignore it. Do it the most efficient way, okay? Pull all the tools out and attack it that way. Because I want you to get to the point where, yes, you can do integral test. You need to practice it. But end of day, the best method is the method you want to use. So, yeah. If it converges, what's the sum? No, usually I hint enough that you kind of know. Like, let me see. We like looking at old exams, although I don't know what kind of difference it makes at the end of it all. Let me see if I have my exam 3. There it is, 10 problems. Find the sum. So you know that that's got to be what? What type of series does this have to be? Or telescopic. This is either geometric or telescopic. My guess is telescopic, right? Partial fractions. If you do partial fractions first, turn it into subtraction, you're in business. Next one, find the sum. This is a geometric series and a geometric series. There are 2 different geometric series being added together. So there are 2 different R's. You have 2 different sums and you put them together. But find the sum. That means it had to be geometric or telescopic. Now, notice, does this converge or diverge? What do you do with that? That's the question you have to ask yourself. You know, are you going You're going to use a comparison test, a limit comparison test, integral test. Use the integral test. Okay, so I did direct them to use the integral test. But if you were going to do this now, how would you do this now if I didn't tell you to use the integral test? What would you use? Limit comparison or comparison, right? That would work out real clean. Does this converge or diverge? You actually have to come up with the formula for this one first. So what's happening on top? Odds. So maybe what? 2n plus 1 would make the odds on top, and on the bottom? Isn't that 2 squared, 3 squared, 4 squared, 5 squared? So starting at 2, I need to go n plus 1 squared. So that, plug in 1, I get 2. Plug in 2, I get 3. So shouldn't this do it? Which, if you rewrote it, 2n plus 1 over n squared plus 2n plus 1, how would you do that problem? Comparison, right? When n is big, this acts like what? 2n over n squared, which is harmonic. So this behaves harmonic. I would do a limit comparison with a harmonic series on this one. Just giving you a feel for the test that I've given in the past. All right, does this converge or diverge? Does it converge? Absolutely. We need to talk about that next. This one. Does this converge or diverge? Oh shit. We haven't seen factorials yet, have we? Okay, we need to get good with those. Converge or diverge? Oh wow. And up here and in here, right? And then all of a sudden we throw x's in here. Now this is where we get into what are called power series. Anyway, okay. Give you some idea. All right, next note. Alternating series. All right, I'm going to look at the very bottom, the last thing here, very bottom. This says that if the sum of the absolute value, right, of a series, of a sequence converges, then the series itself without the absolute value converges. If this absolute value converges, we say this series is absolutely convergent. Or we could say it converges absolutely. The absolutely there is, you know, when we say absolutely, we can kind of misinterpret it sometimes. Like, do you like ice cream? Like, absolutely. You know, that means like that's a very strong way of saying yes, right? Absolutely here just means absolute value. Okay, it's not a stronger form of convergence. It's just a certain type of convergence. So when we say, if you're looking at some series, right, like we were looking at an alternating series, here it is. If we forget the alternating part by taking the absolute value and wiping out the alternating part, if that series converges, then the original one had to converge. And in that case, we say it's absolutely convergent. So let's take a look at an example. Maybe this will start to make sense. Example. Converge or diverge? Absolute convergent? Yes or no? So does this converge or diverge? All right, so let's take the absolute value. The absolute value of this of the sequence inside makes the -1 not alternate anymore, doesn't it? The absolute value of -1 is always going to spit out a 1. So isn't this exactly the same as this? Which is what? It's harmonic. What is harmonic? What does this harmonic do? Diverges. So what does this thing up here tell us? If the absolute value of the sequence, if that series converges, the original one had to converge. But it didn't converge. It diverged. Does that mean that it diverges? No. It just means that that didn't tell you anything. Is it absolutely convergent? If the absolute value of a series converges, we say that the original series was absolutely convergent. Did the absolute value of this converge? No. Okay, so it's definitely not absolutely convergent. But that still, we weren't able to determine if this converged or diverged. Does it converge or diverge? We did this already, didn't we? We did this problem just a second ago. We used the alternating series test, didn't we? So we already saw that. When you do the alternating series test on this, that gave us, what was it? Convergence, right? So it is convergent. Is it absolutely convergent? No. Next one. How about this? Sum -1 to the n over n to the third. Same questions. Converge, diverge, absolutely convergent, yes or no? Okay, working quickly here because time. Let's just figure out, does it converge or diverge? What are you going to use on this to try and figure out convergence or divergence? Alternating series? Okay, that means you have to show that a sub n is greater than or equal to a sub n plus 1. And you also have to show that the limit then goes to infinity of a sub n equals 0, right? What is a sub n for us? 1 over n cubed without the negative part, right? So we need to show 1 over n cubed is greater than or equal to 1 over n plus 1 cubed. And I'm just going to put a check mark next to that, dot, 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 check, meaning you could multiply that out and convince yourself that's true. And then what about this part right here? Is this true? Yes. That's true. So what happened? What is our conclusion? It's convergent. Could not. Very good question. You could not do P-series because P-series requires you to, well, it can't be alternating. All right? So the answer here is it's convergent, right? Now, is it absolutely convergent? So to do that, we take the absolute value of what's up there. So take the absolute value, which is just 1 over n cubed, which is a P, that one is a P-series. P is 3, which is bigger than 1, and what does that mean? Converges. Therefore, the original series is absolutely convergent. That's what I want to draw. Make sure that's a theorem. What's on here? I want us to see the two. Yes, I'm about to answer that. Okay, so let's just kind of summarize here what happened with those two examples. The first example I gave us, we had a series, right? Was it convergent or divergent? No, the first example, the -1 over n. This one right here. Look. It was a convergent series, right? Did it converge absolutely? No. So in this one, it was convergent, but not absolutely. This one that we just did was convergent and was also absolutely convergent. So just because you're convergent does not force you to be absolutely convergent, right? So being convergent is not enough to determine this, is it? What the last thing on here tells you, though, this is a theorem actually, is that if you are absolutely convergent, then the original series must be convergent, which can be very powerful. So look at this. I'm going to restate this problem again right here. The problem we just did. Now using that theorem. I want to know what that one's doing. So I look quickly, what's the absolute value of that? 1 over n cubed. It's a P-series, isn't it? P being 3, and that converges. This theorem says if the absolute value converges, the original series converges. So I don't have to do an alternating series test. That's how you would properly use this last theorem. So the way I would write this down is I would say, this right here, absolute value, equals this, which is P series, P3, convergent. Right? Therefore, the original series converges. So if the absolute value converges, you're guaranteed that the original one will converge. Now you must be careful, because what about something like this? You break out the absolute value, you try it real quick. What would the absolute value on this thing yield? I'm going to write that as n to the 1/2. Is that good? One over n to the 1/2. What type of series is this? P series? P is 1/2 is less than 1. What does this series do? Diverge. Well, the absolute value diverges, right? What does that tell you about the original series? Nothing. Theorem here on that page says if the absolute value converges, you're in business. You don't have to do any work. This would tell us nothing, which means that in order to do that problem, you would actually need to break out the alternating series test and go with it. All right? So you need alternating series test, ... I'm not going to work through that. All right, next test. And this is a big daddy right here. You're going to find that as we move through the next section, this is the test of choice for what we're going to be doing. The ratio test is going to be broken out all the time, seems. So what does our little cheat sheet say about ratio test? You have a series. You're going to take a limit. All right? You're going to take a limit. But you're going to take the limit of a sub n plus 1 over a sub n. Notice that it's very much like the limit comparison test that we had earlier, where we did a limit of a ratio, right? Except that you're not comparing it to anything. Well, you are. You're comparing it to itself. So, you know, a sub n plus 1, if you're looking at it in your series, you know, if you pick some place out here, a sub n plus 1 is the one right next to it, isn't it? And what you're looking at is the ratio between these two. And what you're hoping for convergence, what do you need? You need, oh, it's absolute value also. You need this limit to be, they call it L. If that limit L is less than 1, that means that the ratio between these two is small, right? It's a fixed constant. And so they're not getting very far away from each other. And that gives you the convergence. Again, I'm not proving the ratio test with, you know, precise math, but I'm just trying to visually, like, what's happening. The next guy away is not getting real far away from the one in front of it. Since they stay together, they stack up nicely and you get a convergent series. So if L is less than 1, not only convergence, but what? Absolute convergence. Remember, absolute convergence implies convergence. So this is a big result. Absolutely convergent. This is all on here, right? If L is greater than 1, and notice also it says, or infinite, okay? So infinity is okay to get here. Then it diverges. Go over to the comments section. It says what happens if L is less than 1. It says what happens when L is bigger than 1, but what if L is 1? The test is inconclusive. Also, it gives you a hint. This is very useful when you have factorials or nth powers. If a sub n is greater than 0 for every n, disregard the absolute value. So if your series terms are positive, you don't need the absolute value there. So you want to do that test problem I gave my class? Yeah, you could use this on a geometric series. But if they're asking you to find the sum, you would want to go further with, this would only tell you it converges or diverges. It wouldn't actually find you the sum. That's right. That's what I was saying. Now that you've seen, like we're getting to the end of these tests, now that you see that, as soon as you see me say find the sum, you know it's one of two things. Where's that exam? Let's try this one. Oh man, this we may be biting off a little more than we want to chew right now. God, that looks kind of like a nightmare. I think I'll make this the next example we do. Oh well, I'm not going to have time. I'm going to have to pick something a little bit less intense for our first problem. So let's go with, I'll just make one up here. We'll make the bottom n factorial. I want you to, or do you want to do n factorial? Let's do n factorial on top, sorry. Let's do that. We haven't done a factorial yet. The first thing I would do here is try and figure out what's happening with nth term test. And you get infinity over infinity. And then you can't use L'Hopital's rule because you can't take a derivative of n factorial. So you probably have to go nth term. I don't even really know right now what happens. But as soon as I see the factorial, I'm thinking ratio test. So here comes ratio. A sub n in this problem is this, right? That's a sub n. And so I'm going to set up a limit. I'll let n go to infinity. Absolute value now. Do I have to put absolute value right now? Said if the terms were positive, I didn't have to, right? But I'm going to put it because I do not want you to ever forget them. Absolute value is always here on ratio test. Then I'm doing a sub n plus 1 over a sub n, right? That's the ratio I'm about to set up. So I have to plug n plus 1 in here, and then I have to plug in n and put it underneath. So let's do this. N plus 1 factorial over n plus 1 raised to the n plus 1. Oh, wow. Okay. Over n factorial over n to the n. All of that in absolute value. You're going to get the flipping to happen, aren't you? And we're going to see as we move into next week that we're going to get so used to that flipping that we're actually going to flip it the first time we write it. We're not even going to write this ratio. We're just going to write it as flipped later as our first step. So what is on top? We have an n plus 1 factorial up there, right? What came and joined it? N to the n over. On bottom, we have an n plus 1 to the n plus 1 times, what's down there with it? What is it? N factorial. I don't really need the dot. There we go. Crap, I got to figure out what that is, right? But remember with the n factorials, the property, we could like peel one off of this and get them to cancel, couldn't we? So in an effort to save space, and because time is now an issue, right above this I'm going to put n plus 1 times n factorial, yes? That's what that is. And that will be able to cancel out, I'll be able to cancel out that right there. And then on the bottom, I'm going to rewrite this as n plus 1 to the n times n plus 1. Do you agree that this is the same thing? N plus 1 to the n times n plus 1? Because that's like a first power, and I add them together. I'd put these together, I'd add the powers, I would get this. Nope, it's times. Just like you write, 5 factorial is equal to 5 times 4 factorial, right? All right, so my canceling here, I only got one thing to cancel, and that was it, right there, the n factorials. So let me see what I'm left with. I have a limit as n goes to infinity. What's still upstairs there? Oh, wait, didn't I get an n plus 1 to cancel? I didn't see that. Do y'all see that? Doesn't this n plus 1 and this n plus 1 cancel? I'm sorry, I didn't see that initially. Those cancel. Okay, so the only thing left upstairs is n to the n, and the only thing left downstairs is n plus 1 to the n. Y'all still with me on that? And since these are both raised to the n, can I put them together in a fraction? N over n plus 1 to the n. Let n go to infinity. What does the inside do? Okay, so you would need L'Hopital on that, wouldn't you? And that would go to 1, wouldn't it? So the base wants to become 1, and what does the top want to become? Infinity. That's an indeterminate form. So it's okay, that's why we took Cal 1. So we go back and we say, how do we deal with that form? Well, we call the left side something like y. I'm just kind of saying, I'm going to start this over. Not over, but I'm just going to write this down. And now I try and figure out what that is. So we put the y so that we can bring the natural log in on both sides. Natural log y equals limit n goes to infinity. We're popping a natural log in here, right? But that allows us to drop the n out front. So n times natural log n over n plus 1. You know what? You remember what we did now? Put that n in front of the log down on the bottom as a 1 over n. Good. Most of our ratio test problems are not going to turn out to be this long and drawn out. And now when you let n go to infinity, you should get 0 on bottom. You should get, let's see, we said that was 1, but natural log of 1 is 0. So now you have 0 over 0. Now you can use L'Hopital's rule. What a mess. I'm out of time. Think you could finish that up, right, yourself? Do we care what it is? Has anyone got to it yet? No? I'm curious, though, is it a finite number or not? If that number turns out to be less than 1, this series converges. If it's greater than 1, it diverges. You have a lot of homework. Have a good weekend. If you need to talk about your grades,